Happy to have Sam Buchanan with us today. Sam is just finishing his 2 years minus a week or something like that here, minus a few weeks, and is now looking for exciting new directions to work on, and in fact will tell us about one of those that. Looking forward to hear what you tell us. Thank you.
Thanks, everyone. So first, let me briefly apologize. So I wanted to talk about some very new, hot off the press work today. And if you saw the original talk announcement, it was maybe suggesting something different. Unfortunately, with this hot off the press stuff, sometimes things are a little bit too hot, and so I wanted to let that work settle a bit more. And today I'm going to talk instead about something that's a little bit more stable that I've been working on with some folks from Berkeley and other institutions over the last 2 years. And this is some work that's thinking a little bit about kind of a little bit, now maybe we call them classical ideas from high dimensional data analysis, information theory, optimization, and what relevance those have in kind of this deep learning era of convergence on transformers and an era of representation learning. So I'm going to be talking a lot and thinking a lot at a high level of this talk about representation learning. So I'd like to kind of start from some, or to me, maybe canonical examples of this. And so one that I think is tractable and also interesting enough to be especially worth mentioning here is kind of this sparse coding problem, where you are kind of sort of assuming that the universe is giving you measurements by some process of some vector z, which is sparse. So you don't really know what z is, but you know that it's sparse. It can be described with a small number of non-zero entries out of sort of possible, it could be supported on observation space. And this interesting sparse coding problem has the upshot of you being able to, from these measurements, it's been very lossy, perfectly reconstruct the original sparse vector if you know how it was measured, using sort of efficient algorithms like convex optimization. And by virtue just of the fact that you know that the underlying signal is sparse, so knowing the structure of the data, you can reconstruct it efficiently even from the structure. So as a representation learning problem, you can think of this maybe as for structured signals measured with respect to a sufficiently incoherent basis. It's possible to sort of learn representations for these signals, even if they're very high dimension. And so the interesting thing maybe about the sparse coding problem and sort of algorithms around this problem that were really in vogue maybe 20 years ago before the stage. It's something that I like a lot about it. It's just that you have this nice interaction in between kind of theory and computation with this problem, where because the algorithms that you're using to solve and reconstruct and model here are so kind of simple and tractable, you can actually prove that they work under certain natural models for the data. Based on that kind of mathematical analysis, you can also develop algorithms for data that has different types of structure, not just sparse, but maybe dimensions of low dimensionality. And you can see those algorithms, work to some extent, not to maybe the extent that we would modern era, but algorithms that can really work in cases where the structure is there. And so there's this nice symbiosis in between theory and practice of this model, which is something that's really cool. And you can elaborate this a bit as well without going outside of tractability. Yeah.
So just sorry for being petty, but I'm just trying to parse what's going on here. Should inside the log, should measurements be dimensionality?
So in this case, I'm just asserting in the classical sparse coding problem that the number of rows of A only needs to be this large in order for you to solve this problem.
So measurements is how many dimensions are in the signal, and sparsity is how many non-zero dimensions are, correct?
No, in this case, n is the number of dimensions in the signal.
But the word measurements, is it a
inside
number?
the log. The measurements inside
Measurements
the log.
is m.
Right, but inside the log should it really be m, not n?
You're right. That's a mistake. It should be
Okay. This makes more. Okay, just to make sure we're on the same page in terms of what you're talking about.
So the point is just that what you really need is essentially a number of measurements that's proportional to the intrinsic information content of the signal. mention all the entries. And so you can elaborate this as well, going to cases where maybe you don't actually know the basis in which the signal is sparse. You can simultaneously learn that basis and the representation coefficients. And this problem gets harder even though it's still quite a simple model. You can still prove in some representative special cases that you can reconstruct the data. So again, these sort of sparse coding models, or this model where you learn simultaneously A and the sparse coefficients, is called dictionary learning. There's nice symbiosis in between theory and practice. That's not something you often see in sort of the case of using deep learning algorithms in the modern era. But we really need to use deep learning because when we want to go beyond these sort of simple models for data, sparse signals can be like linear or piecewise linear structure. It's sort of a very restrictive model. If you want to actually throw your data processing algorithms at data from the physical world, you want to be able to perceive and maybe even interact, you really have to cope with low-dimensional structures, which of course is still there, but low-dimensional structures beyond these simple linear structures. So really coping with nonlinearity is maybe one way to argue that it becomes very essential to have more powerful algorithms for processing data, especially deeper representations coming from deep learning and algorithms like this. Yes.
Why are you saying that the low-dimensional structure is of course there? How do we know that's true and why?
It's true because there's, like if we're perceiving measurements of the physical world, there's structure in physical environments, built environments, natural environments. It's different from, unstructured measurements.
The structure specifically is manifested as some intrinsically low-dimensional something.
Yeah, maybe so you could think of it as like statistical correlations as well from this perspective. But I will argue that both of these can be thought of as kind of a low dimensionality in the measurement. But if that makes more sense, that statistical correlations is maybe one way to look at it. Redundancy due to the structure in the environment. And this is something ubiquitous, and so one way I think to think about the success of deep learning on such nonlinear data with significant low-dimensional structure is just that it can really capture these more flexible types of nonlinear. So one of the most popular architectures that we're using these days to do this is the transformer. And so I'll talk more about transformer later in the talk, reviewing the exact structure in case it's not totally familiar. But what I want to just emphasize now at a high level is this really impressive kind of convergence among different deep network architectures used in different tasks, different modalities of data. So across all these different text, language, even sometimes embodied applications, it's becoming more and more common to see this one neural network architecture, the transformer, being really high performant, flexible, very well adopted in these different domains. But there's maybe some things we might like to do better. So the transformer is excellent, scalable, getting very good performance. But because of the fact that these architectures, so I won't use this terminology too much, but just to go with the title of calling something white box, I think of architectures like the transformer as being black box, in the sense that their design is very empirically motivated, sort of motivated in order to run fast on the hardware that we have, motivated in order to perform well on the metrics and tasks that we care about. And so when you want to understand at a deeper level some of these very interesting phenomena that arise on the transformer, that maybe don't arise immediately in previous sorts of machine learning, like this in-context learning paradigm. It's challenging because the black box design of the network makes it hard to know what exactly, what internal mechanisms in the computation of these transformers are responsible for these very interesting emerging. So models where you understand a bit more about the internals could be helpful. And of course, there's always the motivation of safety as well when you don't understand perfectly computation that's being done internally by the model, maybe only at the level of the input-output. There can be sort of safety, security risks, and these become more and more urgent if, as these models become sort of the capabilities better and better, and they're adopted in broader and broader areas. So both of these sorts of considerations maybe motivate thinking about alternate paradigms than just sort of black box architectures. And so what I'm going to talk about in this talk is just maybe one really high level sort of line of thinking around what it might look like to take some of these old ideas from high dimensional data analysis, and I'll talk about a few more information theory and optimization later on, and see if those can be used to understand what computations an architecture like the transformer might be doing with respect to the data. So I'm going to talk about this kind of through the lens of thinking of transformers, architectures like this, as performing representation learning on high-dimensional data with respect to just sort of an abstract model for what that means, and sort of the essential computation that's being performed by these networks as trying to represent and transform low-dimensional structures in the high-dimensional data towards more compact, useful representation that can be used for downstream processing. So this type of a paradigm is kind of going to be the organization around which I'm presenting the rest of the developments of this talk. And kind of the outline, building up from some of these ideas from high-dimensional data analysis will be, first I'm going to talk about kind of how to measure the quality of a representation in sort of an abstract way by some objective function. And then I'll talk about how to take such an objective function and then interpret it or reinterpret it, let's say, as an architecture of a neural network via this simple idea of unrolled optimization. So optimizing objective functions will correspond to kind of layers in the network. And we'll show in a certain simple instantiation of one such optimization algorithm with one such kind of objective function for quantifying representational quality. That you sort of interestingly get out of this process an architecture that looks a lot like the transformer. And then I'll show some experimental results that demonstrate that the architecture that you get can scale well, scale not poorly, and also has some interesting side benefits as well, maybe weren't present immediately in the original transformer. So by this process, just trying to argue that there's something interesting to hear in terms of, interesting to understand here, kind of as a theoretical framework, and it can even give you some interesting practical benefits. So it can be productive to think along these lines. Okay, so the high-level conceptual idea that I'm going to build off of to kind of instantiate this objective function that measures the quality of learned representations is coming from like a basic inspiration in information theory. And kind of the intuitive justification here is that so algorithms like sparse coding, dictionary learning, these are good. They're a little bit parametric in some sense and good at representing kind of linear or piecewise linear structures in high-dimensional data. But if you want to be able to represent more nonlinear low-dimensional structures, you need like a much more flexible model. And it's maybe not immediately clear what that should look like. So we're going to try to take inspiration from some ideas coming from information theory, which in many cases are applicable to kind of general distributions of data. And the idea here is just going to be that the process of representation learning is trying to incrementally reduce the coding rate of observed data in kind of a pursuit of low dimensionality. So we're not going to be ever computing directly things like the coding rate. We'll show some tractable approximations that kind of instantiate this type of paradigm. So indeed, kind of maybe the information theory way to think about whether or not a representation is useful or kind of good is to kind of quantify, to think about kind of taking the observed data and coding it with respect to some code book. And what we want to do, kind of thinking about this classical rate distortion framework, is find a code book for the representation that minimizes the coding rate subject to some specified distortion. So there's some accuracy or kind of this distortion, rate distortion trade-off here that maybe quantifies how compact the code representation is, subject to some allowed tolerance. And then we won't go too much into the math here, but there's these classical relationships between, on one hand, this sort of kind of coding rate perspective, and maybe in sort of a statistical perspective based on the mutual information. So these are kind of two sides of the same thing. So for our purposes, we want to try to make this kind of abstract idea more computational. And so we're going to start from simple models and then kind of try to build that out with something that's applicable to more general nonlinear structured distributions of data. So the simple model, kind of an analogy to the piecewise linear sparse structure, can come in as like thinking about Gaussians in the statistical setting, or mixtures of Gaussians. And so what we can sort of find is that, like, although in general, kind of computing codebooks that optimize the rate distortion function, general distributions of data, is like an intractable problem. If you're sort of coding certain simple distributions of data, like for example, just the Gaussian, you can get pretty tight approximations to this rate distortion function. So this classical one that's shown on the slide here, this is kind of trying to code some observed data arranged into like columns of a matrix X. So I'll mostly do this convention in the talk of putting the data samples as like columns. So coding that with respect to a zero mean Gaussian with unknown covariance. And so if you calculate the rates of distortion for that, what you end up with is this nice expression that looks like it's, and so it's very much related to kind of the volume of the covariance ellipse that's associated to that data matrix by this log determinant. But so the point here is just that we have this kind of closed form expression, or if we want to calculate the coding rate of some data with respect to a Gaussian source, so we can do that with this expression. And then the idea that we're going to use in order to kind of build this idea out into something that can help us identify low-dimensional structure in data is to kind of leverage this simple idea, which I think appears in a lot of different contexts under different guises, which is kind of like, so we'll call this like a notion of information gain. So the basic idea is that, like, if you have a model, some type of a model for a low-dimensional structure in the data, and it could be anything. So the example that I'll illustrate this with on the next few slides is kind of just like a clustering model. Where so you have like this big matrix X of data samples, and maybe you're just trying to cluster them into different classes. So the clusters there are kind of the dimensional model. So the idea is that if you want to discover interesting structures, I'll call low-dimensional structures, in this overall data set, what you can try to do is find clusterings of the data, or find sort of more generally like models for the structure in the data, such that when you code the data overall, and then you compare the cost of like coding the data with respect to the model. So like in this example, just like clustering the data and adding up the coding rates for each of the individual clusters, you have a very large difference, or maybe as large a difference as possible, in between the cost of coding with respect to like this null model, just coding everything, and the sum of the coding rates for the different clusters, or the different components of the low-dimensional structure. So what you can try to do, in order to discover like useful low-dimensional structures for explaining the data, is try to find models that maximize this difference. So in this simple example, just talk about partitions, but we'll make this more general later on as we try to connect this to transformer. So the example of what this looks like in the context of this Gaussian rate distortion approximation in the case of clustering. So if we imagine a setting, just for example, where there's k different clusters and sort of denote by subscripts these different partitions of the overall data matrix into like submatrices associated to each cluster. And what we can do in order to calculate this kind of the cost of coding with respect to this model for the structure of the data, because these partitions are all disjoint, we just sort of take the relevant submatrices and add up the coding rates for each of those. So we get this expression RC down here, which is essentially the same as what you get if you just took the coding rate for each of those individual matrices Z sub k. And then if you want to calculate the overall information gain here, you just now take the difference between the cost of coding all the data, this first term R of Z here, and the cost of coding the data with respect to each of these clusters, the sum of those. So that gives you a notion of information gain for clustering the data here. And the way to actually take this and try to make it a little bit applicable to more general distributions, at least maybe the most naive way, is that so rather than so the limitation here, like we talked about before, is just that so coding data with respect to this kind of Gaussian cluster model only works well if the data really follows this Gaussian cluster model. So we want to be able to apply to more general distributions of data with different like nonlinear low-dimensional structures. And so one way to do that is just to think of this, that like having some representation function, z theta, a parameterized summa, like a deep neural network, that actually maps from the observed data itself, some samples x, to a representation z. And then we try to learn a representation z via that mapping that actually maximizes this information gain. So this is maybe the most naive way to try to take this measure of information gain defined for Gaussians and actually extend it to more general distributions of data. So just by a parametric mapping, like a neural network, it maps data into a representation, which then is we maximize the information gain of that question.
So you said you map it to some space, but in that space you didn't say explicitly something, but like in that space you consider it as Gaussian, so you map it as if it's Gaussian in the map space? Okay.
Yes.
Okay.
So at least at this level, no further. Other question? Yeah, so this is maybe just the naive way to take this idea of information gain for Gaussian distributions or piecewise Gaussian and then extend that to more general distributions. So the reason why this is not totally not sensible maybe is that it turns out that this information gain objective function, it does have certain nice optimization.
Sorry, I'm still a bit lost here. You said you have a neural net, but the neural net maps from the inputs to this Gaussian space or the other way around?
From the inputs to this Gaussian space.
So why wouldn't they just collapse everything to a single point? Wouldn't that optimize your metric?
I don't think so, because a single point, well, okay, so we should think of having appropriate normalization in the representation space. So at least like things are uniform. But in that case, you want to make the information gain as large as possible. So actually a single point doesn't make that as large as possible. Actually having more diverse representation is a bit better there. So if everything was a single point, I think the difference would be zero.
Okay, fine, but like to
So actually you kind of want
to degenerate into a bunch of random points though. But the point is you can forget the input. Like if you're not required to this map to be vertical, you can just completely forget the input.
That's true. And that can be a problem. So we're not doing full autoencoding. But I mean, I think this type of a paradigm is pretty common in a lot of self-supervised learning approaches. And so I don't think it's necessarily like this type of a learning paradigm. I wouldn't say this is something that breaks this.
Okay, I guess I'm a bit confused with what this is trying to capture. Because you're not getting an encoding for the data this way. You're not representing the actual data. You're not getting an actual encoding or representation for the data.
Yeah, I think what we're trying to do maybe is like promote learning a good representation for the data. So I'll talk about why this objective promotes that in a second. But I think I see your concern. So there's a little bit of a detachment there. But the reason why this might be a sensible objective, so you can sort of study its optimization landscape, I think. And so this is just a coarse characterization theoretically. So there's some technical assumptions that are kind of mild, not shown on the slide here. But if you sort of look at just the optimal points of this rate reduction objective function in this clustering set, so this is the setting where you're like provided with kind of the labels of different data samples that constitute the the partition of the data into different classes here. That's this pi matrix. And so think of optimizing this objective function subject to a scale constraint. So things cannot be like blown up because that would change the objective in sort of a trivial way. So what you actually find is that the optimal points of this objective function, so given enough samples here, are actually sort of corresponding to like mutually orthogonal and as isotropic as possible subspace arrangements of the data that are in line with those partitions stipulated by the matrix pi.
Sorry, it's possible that you explained it and I missed it, but so the classes are different types of data. They are, you assume that they exist, but they are not given any labels about those, right? That's self-supervised.
No, in this case, this is actually a supervised setting. So
okay.
So we will go to a self-supervised setting.
Okay.
But
So
for now,
and you assume that this class is, and the number of classes, it sounds from that result, if you go back to the next this slide, if I understand correctly, the number of classes is at most the number of dimensions because each class has to have its own subspace
for this result.
Just
I think some analysis can be done
What's an
more generally.
example of that scenario? It seems very strange to me.
You could just think of them as like a very coarse categorization of the data, rather than like ImageNet level of dog breed specificity. C-form classes or something like this, or MNIST digit classes, like a simple distribution of data.
Can you go back to the previous slide? So maybe this is also, I guess, what I missed, that the clusters are
previous two.
the objective there, but you're
Yeah.
so where's the fact? I'm a bit so how are the classes given here? I'm a bit confused because it looked to me like you're summing over all the classes there.
That's true.
But the data is somehow partitioned. Is this Z?
This
When you write
objective
here
ignores
C,
the
is
class.
this-
Oh,
yeah.
C is class?
Where is the class? Where does the class appear in there in that objective?
So in this objective, I'm writing this matrix pi as like a diagonal 0-1 matrix that just sort of says it's like 1 on the diagonal if the sample belongs to this class.
Oh,
and
I see.
0
So you're not optimizing over pi.
Yeah, sorry, I didn't explain that, but no, we're
You're
not.
taking pi. Okay, I thought you optimized
Taking
over
this
pi.
as
You're
fixed.
taking pi as given.
Okay.
Okay.
So we'll show some ways to do sensible treatment of
Okay. That
Yeah, thank you.
pi is given. That.
Yeah, so this is like a supervised special case. If that
Oh,
makes sense.
that was I think my confusion. Sorry if I missed that.
So that makes things much easier. And so under that type of a setting where you have these labels that partition and things are sort of given to you in like a sensibly scaled way, you can actually prove that the optimal points of this objective function correspond to matrices Z, where you have sort of like mutual orthogonality in between kind of the submatrices that are associated to each of the different classes. So these are now denoted by the Z subscript K, and those can also be equivalently denoted extracting the relevant part with these pi matrices for each class. And they're as isotropic as possible. So that's not shown on the slide here, but it's like those Z sub K stars are not collapsed down on any of the directions within that subspace. So they're well spread out. So actually this objective function in its own way is actually promoting you via its optimal points to learn kind of well-distributed representations that are not collapsed for the different classes. And so as was commented, this is all in this supervised setting where you know those classes. But so this objective function, this is actually a good property to have with respect to kind of a lot of considerations in self-supervised learning objectives. So you pay maybe a bit more to compute this objective. A priori, you're taking some volumes here. But the trade-off is that you actually get something that actually is promoting non-collapse and promoting learning diverse representations. So even though, so if you go and learn like a representation Z theta as some deep neural network that maximizes this information gain, nothing is strictly promoting you learning a good representation or a good codebook of the data. But still this objective is somehow implicitly giving you some nice properties for the optimal representation. It sort of justifies at an intuitive level why it might be useful here. But so I think we want to do a bit more here because from the perspective of understanding the computation that's going on inside our deep networks, we don't want to just maybe take a black box network, a ResNet or transformer, what have you, use that as our Z theta, and then learn the parameters of that network to optimize this objective function. Actually, we can, and it helps in certain applications for sure. But from the perspective, this kind of fundamental perspective of trying to understand better the computations in these deep networks, we might want to know more. And so what we'll try to do towards kind of addressing that gap is actually use this objective function to derive the architecture of a deep network itself, instead of just using a kind of an empirically designed deep network. And so the basic idea that we're going to adopt for that is this idea of unrolled optimization. And so the example kind of shown on the slide here, just explaining this idea. You may have seen this before, but if you haven't, it's pretty simple. So unrolled optimization just takes like some objective function, like here thinking about this lasso objective function for sparse coding that we talked about at the start of the talk, and then writes down like an optimization algorithm, like an iterative first order, let's say, optimization algorithm for optimizing this objective function. So for example, if you shuffle things around a bit for the sake of kind of being evocative, like doing the proximal gradient descent algorithm on this lasso objective gives you an iteration that looks like this update down here. So you are kind of doing a computation that looks very similar to the computation in a feed-forward neural in this proximal gradient descent method. So alternating like this sparsifying element-wise nonlinear function and this shifted ReLU here with a linear transformation of the data. And so in the case of this unrolled optimization, like the operators that you get in this like neural network that corresponds to the iterative optimization algorithm, they're like related to the original objective function that you wrote down. So in the case of the sparse coding, like the operators for the linear transform come from the measurement matrix or the sparse dictionary, and the nonlinear function comes from like the fact that you're trying to sparsify this sparsifying prior. So this is like a way, maybe originally, to enforce some prior knowledge you have about your data or your measurements, etc., in the structure of a neural network with that data. But like in a more general sense, kind of going kind of maximal, I guess, on the unrolled optimization perspective, what this can say to do is just to like, so instead of thinking of this iterative optimization algorithm as something that you want to run to convergence in order to get the solution to your original optimization problem, you just think of it now kind of like a neural network and truncate this iteration after maybe 12 iterations, so just some number of layers, something like this. And then for those parameters in the resulting network, you pick some auxiliary objective function and actually collect some data and train on that objective function in order to learn the parameters of that truncated network. So this starts from this objective function, gives you a neural network architecture, and then once you have it, you sort of just train on whatever task is relevant or whatever objective is relevant to the task you're trying to solve in order to learn the parameters of that. And by virtue of the original derivation, you can maybe understand some vestige of the original kind of structure. You can understand something about the architecture of this network that you get and that you train just based on some vestige of the original objective that you sort of started from. So originally, unrolled optimization, kind of as I alluded to, was used a lot in kind of the imaging and sort of the scientific imaging community over enforcing kind of prior knowledge structures like this in deep network architecture. But so what we want to do here is instead kind of use this idea on the information gain objective function. So to derive like a neural network architecture that tries to optimize the information gain. So that's what we're going to do in the next part of the talk. This is going to sort of take us towards transformer. Any questions before we do that? So then let me talk briefly about transformer. So this is a little bit of a paradigm switch in order to get something that we can scale. We are going to, so instead of thinking like in the previous example with the information gain objective of like having a data matrix where the columns correspond to different samples, we're going to think a little bit more like this transformer dominated paradigm these days, and think of each data sample as actually being subdivided into like tokens. And so we'll do the running example of kind of visual data. This can definitely apply to different modalities of data too, just for tractability. And so in the case of visual data, you can think of like originally, so in the previous part of the talk, one column, one sample is an image, and this very naive way of turning an image into tokens, just dividing the overall image up into non-overlapping patches, flattening those patches, putting them in your favorite order, in order to generate, so one sample is corresponding like matrix of tokens. So then each token kind of corresponds to a patch. And so for this transformer architecture, just reviewing this briefly so that we can kind of see a parallel between what we get from optimizing the information gain. You are doing this, so transformer, just reviewing, I guess, is like this neural network architecture where you sort of, and I'll explain this again for the context of visual data, which is a little bit simpler than in the case of language data. So you are taking the raw inputs, these images, turning them, like tokenizing them, so embedding them via some affine map with some extra metadata that is maybe task specific, at this first layer. So that is just taking raw images and giving you out this matrix that corresponds to the sequence of tokens. And then after that, you just have, just like a normal neural network, some sequence of identical layers with different parameters that process the data. But the operators are maybe a bit different from the usual feed-forward neural network operators if you haven't seen these before. So the architecture is like residual style. It has some normalization, ln, but I won't talk too much about that. And then you're alternating these blocks where you do this self-attention with multiple heads operation, which is like a way of kind of flashing the equations, but maybe if you haven't seen that, it might be too much to process first. But kind of calculating correlations between like different projections of the sequence of tokens, and then normalizing and using those correlations to like recombine the sequence of tokens to generate the output. That's what the self-attention layer does at a very high intuitive level. And so in order to make this a bit more expressive, you can take a bunch of different parallel projections of the data and do that, and then sort of aggregate those different parallel projections. That's this multiple head self-attention. So this kind of, when you see it at first, exotic operation is actually a really powerful way to process sequential data, very flexible. So that's the first block in the transformer. And then that's followed by this MLP block with a residual connection, which is just a very simple two-layer feed-forward MLP activation or something like this. You typically go up, increasing the dimension, and then nonlinear project back down. So the transformer just alternates those blocks. And now thinking about kind of this idea of unrolled optimization. So what I said informally in words before, this is just showing it in kind of a flow chart on the slide. So what you're going to do is kind of have a sequence of objective functions corresponding to, so in our case, we'll be using like a small elaboration of the information gain. And then each layer in the network that you're deriving is like taking sort of one step of some incremental optimization algorithm on those objective functions. So each layer is kind of optimizing some underlying objective function. And kind of the design choice of the network that you get out of this is now involved in like what optimization algorithm you use to optimize those objective functions. And of course, the choice of the objective functions. So different optimization algorithms, different objectives will give rise to different architectures. And so this is kind of an interesting design problem. And so in our case, we're trying to do this for representation learning. And so we're going to be doing this on the information gain. So reviewing this information gain, this may be a more compact way to write it. So in the case we talked about in the previous, or earlier in the talk, where we're in this supervised setting where we have some labels for the data, we have this way of sort of dividing, and again, this was in the sample setting rather than like the token setting. So we were partitioning different samples up, coding those partitions, they're all disjoint, so we just add up the approximate coding rates and then take the difference. So we want to take this idea and apply it to the case of kind of tokenized data. So now we're going to be coding like this sequence of tokens rather than like a batch of samples. What we can do in this case, in order to make this a little bit more extensible, is just to introduce some auxiliary parameters, which can maybe be thought of as kind of corresponding to like soft labels for the data. So whereas previously we had hard labels, kind of ways of subdividing, in this context, the tokens into different disjoint subsets. So here we're just going to have a sequence of kind of orthogonal projection matrices UK that we use to project down the data and then adding up the coding rates with respect to those projections. And in the ideal case, so you can sort of see this as a generalization of the previous case, just applied to token sequences. But in the ideal case where these orthogonal projections UK are all like mutually orthonormal, so they're all like not orthogonal but have orthogonal rows, and they're all mutually orthogonal. So this would actually be like a strict generalization to the previous case. This is kind of the case you want to have in practice. But more generally, you can also just have some collection of UKs that may or may not be mutually orthogonal and still sort of work with this objective function. And the other modification that we'll do, in addition to introducing those sort of soft labeling projections, is to explicitly enforce some sparsity of this objective. This is maybe just added for kind of simplicity, tractability. You can also think of it as like having a symmetry breaking effect, inducing a preferred basis for the representation C. But after we introduce that additional term here, we get an objective function that's like the sum, or let's say the difference of the information gain with respect to this collection of subspaces and this sparsity promoting regulator. So we call this the sparse rate reduction. And this is the objective, so applied to token sequences that will unroll in order to see a connection with the transform. So the optimization algorithm that I will talk about is just like a really simple, naive one. So we will take kind of this overall objective, this information gain minus sparsity, and subdivide it into two different terms and kind of do an alternating optimization strategy, optimizing locally approximately one of those terms, then the other, and then repeating. So the first term is just going to correspond to the compression term, this RC. So we're going to do a gradient descent step on that term because we're maximizing the overall objective. So that's going to correspond to like a, we'll see, a compression operation. And then the other term, so after we take that optimization step, we will sort of incrementally, approximately optimize this expansion term RC and the sparsification term. So I'll just refer to that as a sparsification term. So this is going to be our optimization strategy, and we can now kind of work out what these updates, like what sort of, what structure do the resulting neural network operators kind of inherit from these updates. So for the compression term, there's some derivation on this slide here, but it's not essential to totally parse it. The upshot is just that by kind of looking at the gradient of this rate reduction objective, which is not too hard to calculate, it just ends up like the log determinant turns into some kind of a matrix inverse quantity. And so making some approximations, one of which can be justified rigorously, and the other which is maybe somewhat idealistic, let's say, you can actually arrive at an eventual function here, or an eventual operator here, which looks a lot kind of like a linear attention layer, if you're familiar with this, or if you caught Solon's talk earlier in the semester. So this is a lot like a linear attention layer, but the key difference here is that in contrast to the usual self-attention block where you have different projections for each of the different components of the self-attention layer, the query key and value, in this case, all the projections are the same, and they're coming from these matrices UK. They're kind of parameterizing the different subspaces that you're with respect to in the original compression objective. So you end up kind of directly with a gradient term that has this structure. And for the sake of kind of tractability, if you introduce some additional normalization into that correlation term, so you don't have to, but maybe this is something that allows you to get it stable and matches some of the forms that you'll see with, in particular, the transformer. If you apply some normalization to the rows, sorry, in this case, the columns of this this matrix of correlated projections, then you'll get the expression, the approximation at the bottom of the slide here. And so this expression looks very much like the form of the kind of a standard self-attention layer, or sort of for each sum n k, like one head of self-attention. And so just sort of partitioning things up here into different matrices to really parallel with the form of the multi-headed self-attention operator and writing out what we derived on the previous slide. The update that you get from taking this gradient descent step on the compression term, along with appropriate approximations, is something, so we call this the multi-subspace self-attention operator that looks very much like a self-attention operation in the transform, but it's more constrained. So all the query key and value, if you're familiar, projections are implemented by these subspaces that kind of parameterize the original objective function, the UKs, and also the output projection is implemented. So this is the type of operator that you get after making these suitable approximations by optimizing this compression term. So there's this interesting interpretation, let's say, in a little sense, this type of an operator corresponding to a compression objective. So we're optimizing the sparsification term. I won't go too much into the details here, but we make some simplifications for the sake of tractability. So we introduce some additional parameters with respect to which we're optimizing. So kind of a orthogonal dictionary D So we're only trying, when we optimize the sparsification term, not to kind of optimize it with respect to all z, but just to optimize it kind of sparsifying with respect to this dictionary D that we introduced. And so that makes the optimization a little bit more tractable. And after kind of a standard like Lagrangian relaxation, you can turn this into a matrix lasso objective function. And if we want to optimize that locally, incrementally, so what we'll end up doing here is just taking like one step of proximal gradient descent on this objective function rather than trying to optimize it all the way to convergence. And so we talked previously about this update for sparse code. I'm calling this now at the bottom of the slide ISTA, but ISTA is just corresponding to one step of prox gradient on this this matrix lasso objective up here.
That's element-wise.
Yes. Yeah. So element-wise sparsification, along with a linear transformation that sort of corresponds to this dictionary D being applied to the previous the output of the compression block, the CL plus 1/2. So this is the operation that you get through these approximations and through this sort of local update for optimizing the sparsification term. So this is interesting, kind of in contrast to the standard. Well, this sort of parallels kind of the MLP update in the standard transformer. But in this case, there are some differences. This ISTA block is maybe explicitly sparsifying the output. So rather than having like an up projection, nonlinearity, and it doesn't explicitly have a skip connection. The standard transformer residual block does, which allows it to actually explicitly sparsify the output. So when we combine these two updates, the compression update and the sparsification update, we get like one block, this overall unrolled sparse rate reduction objective function. And then if we take several steps on that sparse rate reduction objective, we get several blocks with this parallel structure. So that's kind of how this unrolled optimization idea on the sparse rate reduction objective ends up giving rise to this architecture, which parallels a lot like a transformer architecture. So in particular, like the key difference is just emphasizing those again. And then compared to the multi-headed self-attention block, kind of the multi-subspace self-attention is very similar, but has like shared projections for query key design, and also output as well. And kind of the MLP-like block in this unrolled network, so we call this network crate. So in this case, I didn't show the exact form, but it has the nonlinearity kind of outside, or let's say the residual connection inside the nonlinearity, which actually allows it to sparsify more effectively. So the architecture is transformer-like, but it's actually different. And so to wrap up, I just want to show some quick experimental results that show that this architecture can be trained, it can scale okay, and it also has some interesting benefits we didn't expect in some cases. So the first thing we verify, this one, just a brief mention of this. So we make like a lot of approximations when we go from this original sparse rate reduction objective to the eventual architecture. We did some experiments to check whether the architecture that we get out, this crate architecture, after we train it. So in this case, and in the next few experiments, we're just doing this usual like supervised ImageNet training with the class token scheme in order to learn the parameters of this crate architecture. But so we wanted to check that after we do that training, which doesn't have anything to do with the sparse rate reduction objective. It just, that objective is how we derive the architecture of the network. So verify whether the learned network still has some connection to this objective. And so, we kind of, if we measure the compression term and the sparsification term in each layer, kind of do some averaging, we do see that on average it's going down as we iterate through the network. There's a kind of an interesting connection that remains to the original theoretical derivation. The subspaces in the MSSA layer stay kind of incoherent and things do get sparser, kind of shown on the right here. In terms of the performance, so these are just some like the basic results for train on ImageNet 1K and do some transfer learning. So not training on larger data set. So and this is sort of a smallish scale too, like around 125 million scale. For the crate models, because there's more shared parameters compared to the usual transformer. And again, this is in the vision setting, but because there's more shared parameters, kind of the immediate number of parameters will be less than the kind of the corresponding vision transformer architecture, like with the same patch size and the same layer, hidden dimension, etc. But so here the performance is sort of reasonable. We see some reasonable scaling as we increase the number of parameters, and we're not too far off the performance of the ViT at these smaller scales on ImageNet 1K. And we can show some basic abilities, although I didn't talk about this at all, the modifications that we need in order to train this architecture on text. So the numbers at the bottom are maybe I won't say reasonable yet, but at least it shows that something can be trained in the text domain as well. So this architecture can be used across modalities as well. But I think the results in the vision domain are a bit more engineered and reasonable in the sense of getting close to the performance of very highly engineered models. So something we didn't originally expect that comes out of this is that there's this emergent segmentation behavior as well. So in the self-attention maps of trained crate models, so just trained on, and in this case, kind of this supervised cross-entropy loss on ImageNet 1K data, you actually get this emergent segmentation behavior for free, so without doing any specialized training. I think now, by now, there have been like sort of different discoveries that show like different techniques, both kind of architectural interventions as well as like things to do after training in order to use this emergent segmentation. But some of the original results here suggested that unlike in CompNets, it wasn't as easy to get this ability to use kind of the feature maps of the vision transformer to do segmentation as it was. So it's harder to do this in vision transformers than it was in CompNets. Maybe this didn't come for free. And so some of the original approaches to do this use pretty complicated self-supervised learning methodologies. So very different training setups in supervised cross-entropy training on standard data set. So something about this alternate architecture of the crate model and kind of the ablations show it's actually due to the MSSA layer. So this self-attention alternative with shared projections for the query keys and values. But so this difference actually gives rise to, after you train, this interesting ability to get this emergent segmentation. So that translates into some improvements in downstream metrics as well if we actually use the segmentation maps thus extracted to do some, together with some post-processing to segment different data. So we can scale further as well. So the performance numbers previously are reasonable, but we can improve them further with kind of modifying the design of the architecture. A simple example of this, like one bottleneck that initially appears in terms of scaling performance, like as we decrease the patch size and try to increase the model size and get better performance in these crate models, is was sort of identified as being this ISTA MLP block that we have in crate. In particular, the fact that like we don't have this typical 4x expansion of the hidden dimension that you see in the usual vision transformer seems to constrain the capacity of the crate model a lot. So one way to try to address that is like instead of doing this ISTA block with an orthogonal dictionary, we can use an overcomplete dictionary. And instead of like one iteration of Prox gradient, we can do two. So that ends up looking much more like the usual MLP in the vision transformer. Because this dictionary is overcomplete, it actually sort of behaves like an up projection. And if you down project after you do these two iterations of proximal gradient descent, you get back to the right hidden dimension size. So if we call this like an overcomplete dictionary learning block, we can actually, through this design, get some better scaling performance with it. So allowing it to be more competitive kind of with ViT, and even get on par with scaling up the number of parameters of crate a bit more than the usual ViT. This would be like parameter match because there's these shared projections in crate. But we can actually get on par with reasonable size, still around 125 million, but reasonable size ViT models. So there are ways to sort of continue to engineer these designs as well to make them more scalable. So finally, just one more interesting remark. Kind of in this this sort of paradigm that we've been developing, kind of the perspective is that, or the interesting observation is that if you do unrolled optimization on this information gain objective, and you make some approximations in a judicious way, you get operators in the network that you get that look like transformer. So there's actually ways to make this a little bit more explicit and more constrained architectures, a little bit in an analogy to some of the things we saw in the derivation. So in particular, if you look at some of these recent like efficient attention alternatives, like Songlin talked about, like the delta net and other architectures like this, in those contexts, you can actually show that like by optimizing certain simpler regression objectives, you get exactly sort of kind of attention-like operators in the network. Things like the linear attention this way. So this is a way to kind of make a further connection in between optimization, certain underlying objectives, and layers of networks. Okay, so just wrapping up, this is maybe like a view of one way that one can try to use sort of some of these classical ideas from high-dimensional data analysis to interpret kind of how representation learning is done in deep networks. Use these ideas of information gain, unrolling, in order to like take an objective function for representation learning and turn that into a neural network architecture. And it's interesting that this ends up giving rise to an architecture that's very much like the transformer and even has some interesting benefits. So I think this type of design paradigm can be useful in other contexts as well. And I'm exploring that kind of in a lot of current future work. So let me say thanks for your attention. This was a big collaboration with a lot of different folks. Just give a brief thanks to them. And a very brief final plug. So this talk is a little bit based on kind of a monograph that we've been working on some of these ideas around representation learning, kind of high-dimensional data analysis, classical and modern ideas, in maybe a significantly expanded form. And if this is of interest to you, we're going to have like a full draft of this book, this monograph soon, and I would really appreciate, if you're interested in sharing it with you and getting your feedback. So just thanks again.
Okay, we're almost at time, but if somebody has any questions? Okay, so let's just thanks Sam again, and this is the last research TTIC for this academic year, so we'll see you all back in end of September.